Math 1325, this is our final video of the semester. We're going to be covering the last 10 problems of the review for the final, problems 21 through 30. We left off here with number 21. This is the section of chapter 5 where you're using all the things that derivatives tell us to sketch graphs. And this is the working backwards problem where they give me all the information that came from derivatives and second derivatives, and then I have to match which graph that would be. So I am continuous and differentiable for all real numbers, and that makes sense from all the graphs. They're all smooth curves like polynomials. So it's probably some polynomial graph. They look W-shaped, so there's probably an x to the fourth type of equation. So that's true for part A. Part B, the first derivative is greater than 0 from negative infinity to negative 2 and from 1 to 6. A first derivative is greater than 0 anytime the original graph is increasing. And if it's going to start at negative infinity and go to negative 2, that means it needs to be increasing first, not decreasing first. So graphs A and D are already out. It's increasing all the way till you get to an x of negative 2. And it looks like only graph B is even doing that. So I already know the answer is B. And I didn't even check most of the problem. But we can double check and make sure that all the rest is true. If I check the rest and find something that's not true, then I'm overlooking something possibly. So is it increasing from 1 to 6? This is 1 right here. X equals 1, there's a relative minimum there, and then there's a relative maximum that could be there at 6. So it looks like that's true, that it's increasing from negative infinity to negative 2, and it's increasing from 1 to 6. The first derivative is less than 0 between negative 2 and 1, and that's why it's decreasing between those two. And it's also less than 0, making the original graph decreasing from 6 all the way to infinity. So this is very typical of polynomial graphs. First we're increasing, then we decrease, then we increase again, and then we decrease again. The second derivative is less than 0 in these two sections of the graph, and that would mean that it's concave down over those portions. So from negative infinity to 0, from negative infinity all the way till you get to 0, it's all concave down and bent downward all the way to 0. So notice the relative maximum's at negative 2, but the concavity is still negative past that point. There's a downward curvature all the way to 0. And then it switches to an upward curvature from 0 until an x of 3, about right there. So that would be an inflection point right there. And then when x is 3, then it switches back to concave down all the rest. So there's an inflection point there too. So that covers D and E. The derivative at negative 2 and the derivative at 6 equals 0. That would be this top spot here and this top spot there. The derivatives are 0 there because those are critical numbers and they're also relative maximums. It's also 0 at 1, but they didn't mention that in here. They could have, but for some reason they didn't mention that one. But the derivative is 0 at 1 as well, and that's a relative minimum. And then the second derivative is 0 at these 2 points, and those are the inflection points. 0, 3 is right here. And 3, 4, I guess 0, 3 is lower down right there, and 3, 4 is right there. So the inflection points, they're not horizontal from each other, but that's okay. That's where the second derivative is 0. That's where the concavity is changing from negative to positive or vice versa. So yeah, everything in here is definitely true in B. I didn't find anything wrong with graph B for any of this stuff. And then, so that was the end of chapter 5, was the graphing part. The beginning of chapter 6, the first thing we do there is we try to find absolute maxes and mins, absolute extrema. And there's two main ways this can be done. The easier one is when you have a closed interval. If you have a closed interval, it makes things easier. Then the rule is you got to get your critical numbers, and you check the endpoints and any critical numbers inside this interval. And then you're guaranteed to get both a local, I keep saying it wrong. When it's a closed interval, you're guaranteed to get an absolute max and an absolute min. There could be a tie for the locations, but there's going to be one absolute maximum and one absolute minimum every time it's a closed interval. Because even if there's no critical numbers in this interval, then the endpoints would end up being the two. But at first, we don't know how many of the critical numbers. There can be 3 critical numbers. They might all 3 be in this range, and then I would have to check 5 numbers, and then there's no way to know which ones are going to lead to the absolute max and mins. If you don't have a closed interval, then the second rule is that if you only have one critical number in any interval, whether it's open, closed, or infinite, if it turns out there's only one critical number in a given interval, and if that one critical number leads to a local max or min, then by default it's also an absolute max or min. So we're not going to have to worry about that rule here, but that's the only other way you could possibly do something like this. So my original function is an x to the 4th, 2x to the 4th, minus 144x squared, plus 3. And I only care about the closed interval -7 to 7. So the first derivative is going to give me 3 critical numbers because the derivative of this is going to drop to a third power, 8x to the 3rd minus 288x plus nothing. This is a polynomial. It's never undefined, but it could be 0 3 times. Hopefully 288 divides by 8, because then I can pull out an 8x GCF, leaving an x squared for that part, and then whatever 288 divided by 8 is would be the number there. Hopefully it's also a perfect square too. Whoops, that's something weird happened there. 288 divided by 8 is exactly 36. That's very helpful, because now I got a difference of squares it's going to factor as well. X plus 6 and x minus 6. So there's 3 total critical numbers: 0, -6, and +6. And all 3 of them are in the given interval too. So luckily it's a closed interval, otherwise I wouldn't be able to find any absolute max or mins. So now I'm going to make a table, and I'll put them in order: -7, -6, 0, 6, and 7. I just need to find the original function value of these 5 spots. There's a guaranteed absolute maximum and absolute minimum in these 5 calculations. So first I'll start with, now one good thing is all the exponents are evens. So that means any positive or negative of the same value is going to produce the same answers. So I can just type the positive numbers in. I'll do 2 parentheses 7 parentheses to the 4th power minus 144 parentheses 7 squared plus 3. I'm plugging 7 into the original function, and the answer is -2251. And the -7 would produce the exact same answer, because any negative to the 4th power to the 2nd power equals the same as the positive does. Then I can do second enter and change the 7s to 6s. And so both 6 and -6 are going to have an answer of -2589. Those first 2 answers were so negative, I thought they were going to be the lowest answer, but here's 2 answers that are already lower than that. And then, of course, plugging 0 in is easy because all the x's will disappear. The answer is just 3 if you plug 0 in. So there's the absolute maximum right there, 3. So typically the way this would be written is you would say there's an absolute maximum at, let's do it this way, of 3 at x equals 0. They like the value and the location. Value, there can only be one value. Location, there can be a tie for a bunch of locations where it could happen. But often it's just one location for any given absolute max or min. But our absolute minimum has a value of negative 2,589. And that's the one absolute minimum value because there's a tie. And there's two locations where it happens, -6 and +6. And this is a x to the 4th type of problem, so that makes a W-shaped graph. And since there's a tie here, this is one where both of these are going to the same height. And the x-axis would be in the middle, the y-axis would be slightly like that. So that way this would be a relative maximum, but it turns out to be the absolute maximum in the range. So this is the coordinate 0, 3. And these two local minimums are also the absolute minimums if you just go from -7 to 7. So both, 6, -2589, and -6, -2589. Those are the absolute minimums because -7 would be about here and 7 would be about there. So that's all we care about is we're not doing the whole graph. If we did the whole graph, there is no absolute maximum because the graph goes up to infinity. It would have an absolute, these would be the absolute minimums even if I did the entire infinite domain of the function. But if I only care about from here to there, that's all I care about in my graph. So this is the highest point anywhere in the graph that I care about, and these two are tied for the lowest of any spot on the graph that I care about. They're actually also the lowest of any spot on the entire graph. But that doesn't matter here, so there is an absolute maximum of 3 at x equals 0, and the absolute minimum was -2589. Yeah, I wanted to double check that, -2589, and it was at 6 and -6. And when there's a tie, you just separate answers with a comma. Okay, so that's a good problem there. That is the basic type of problem that you do for absolute maximum and minimum. Okay, next in chapter 6, we did 6.1, 6.4, 6.5, and 6.6. So from 6.4, we did implicit differentiation. And in that section, x was the variable of interest. So I have the equation of a circle here, x squared plus y squared equals 10. And I'm given the point -3, 1. And they want the equation of the tangent line at that spot. Equation of a tangent line, well, slope of a tangent line is the code word for derivative. So I need to take the derivative of this equation, but because it's not a f of x or a y equals, it's an equation that has both x and y in it, then this is where implicit differentiation happens. And at this point, x is understood to be the variable of interest. So I'm going to take the derivative of x squared, which is 2x, and technically there's a dx over dx attached to that, but that just cancels and equals 1. And then the derivative of y squared, if I was doing that one, that would be 2y, but then it gets a dy over dx that doesn't cancel out. The derivative of 10 is nothing. And then you want to solve for dy over dx, because that's the derivative of y with respect to x. That's y prime, that's f prime of x. That's the derivative. If I can get that by itself, that will lead me to the slope of the tangent line. So let me write it better so it looks easier to solve. 2x plus 2y dy over dx equals 0. I canceled this part out. So subtract the 2x to the other side. Divide both sides by 2y. Here's the derivative with respect to x. dy over dx equals, I can cancel these 2's, negative x over y. So this is the derivative with both x and y kind of going on at the same time, although x is the variable of interest. We're going to plug in the given x and y, and that'll tell me the slope at this exact spot. So at exactly this spot, there's a negative 3 over 1, which that double negative would be positive 3 over 1. The slope is 3. The slope is 3 exactly at that spot. So the equation of the tangent line, equations of any line, are y equals mx plus b. Since slope of a tangent line comes from derivative, I got the slope of this tangent line from the derivative, and it was 3. So the only issue is if I want the equation of the tangent line and not just the slope of it, then I need to find the b, the y-intercept as well. But I can plug x and y into this equation too, because this line touches that point. So 1 equals 3 times negative 3 plus b. 1 equals negative 9 plus b. Add 9. And I ran out of room here, but b equals 10. So the equation of the tangent line should be y equals 3x. We already knew it was going to be 3x. And then I now know the y-intercept's 10, so plus 10. And they already have the y equals here, so 3x plus 10. And one thing too is the knowledge of this graph can help a little bit. This is a circle with a 0, 0 center. The radius is the square root of 10, which would be a little bit more than 3. So if you go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, go a little bit more than 3 and draw a circle. Centered at 0, 0. The coordinate negative 3, 1 is right there. And this tangent line would come like this and touch that circle just at that one spot. And what we're saying our answer is saying is that this line has a slope of 3. That could be a slope of 3. It's clearly positive. It's going up 3 over 1, up 3 over 1. And since I'm a little more than 3 away from, no, I'm exactly 3 away from the y-axis, I'm sitting at 1. If I go up 3 over 1 3 times, I'm going to go up 9 over 3, and that's why the y-intercept is 10. So that makes sense that the y-intercept is 10. So that's implicit differentiation. If they don't tell you what the variable of interest is, then it's x, just because that's what the whole textbook was up until this point. The only time the variable of interest is not x is if they specifically state it some other way, like this right here. So dy over dt, that means t is the variable of interest. So therefore, they're relating both x and y to some variable, third variable like t, which probably is time. If some object is moving over time, this is like a physics application here. I have a y cubed equals 2x squared plus 9. So in section 6.4 was the previous problem, then x was the variable of interest. In section 6.5, now some other variable is a variable of interest. Usually it's t. So I'm going to do a very similar thing to the last problem. The derivative of y cubed is 3y squared, just using the power rule. But then I have a dy over dt automatically, since t is the variable of interest. And then I do the derivative of 2x squared, which is 4x, and then that gets a dx over dt. So before, only the variables that don't involve x. The variables that involve x, it's almost like you're not doing this. It just cancels out. So you just do the derivative of x squared normally and put 2x and nothing else. But when you do a different variable besides x, then you get the dy over dx there, or whatever variable it is. Now you basically do that on every variable. Every different variable gets a whatever over dt. And then the derivative of 9 is nothing, so that's all I have. And then what we're trying to do is find dy over dt. They could ask for anything, but they say evaluate dy over dt. They give me dx over dt, and they give me both x and y. So basically, out of these 4 parts right here, I know 3 of the 4. I'm told that dx over dt is 4, and both x and y equal 3. And the goal is to find dy over dt. So I would just go ahead and divide both sides by 3y squared like we kind of did before on the previous problem. Just, you normally try to get y by itself anyway, but that was definitely the one they asked for here. They could ask for dx over dt in general, but okay, so this does not reduce. I could just write it as 4x over 3y squared. There's no way to reduce that. And then I can just put the dx over dt after that. And the goal is to find this, so I don't have to do anything to this. I just have to plug all these numbers in to their appropriate spots. This is 4, and both this x and this y are 3's. Let me double check that I didn't mess up. Okay, 4, 3, 3, yeah. Sometimes you write the problem down wrong and everything you do after that is wrong. It's just a brain cramp mistake, so I wanted to avoid that. 4 times x is 3. 3 times y squared, but y is 3, so 3 squared right there. And then the whole dx over dt equals a 4. So I could cancel this 3 with that 3 if you want to reduce it, and there's no addition or subtraction here. So 4 times 4 is 16 for the numerator, and the bottom is 3 squared, or 9. So the rate of change of x with respect to time is what this is sort of like. The rate of change of x with respect to time, if an object's moving along an xy axis, if it's moving at 4 units per whatever, like 4 miles per hour if it was a car or a bike, in the x direction. It's moving 4 miles per hour in the x direction, exactly at the moment when the x is 3 and the y is 3. And at that exact moment, the y is changing by 16 over 9, a little less than 2. That's an interpretation of this. Oh wait, it says round to 2 decimal places, so apparently they want a decimal and not a fraction. So 16 divided by 9 would be 1.777, so 1.78. 1.78, only because they asked for it. Normally we just leave it as a fraction. Okay, then here's the final thing of chapter 6. This is the related rates, and that's the thing we had the extra assignment on. The shape of a colony of bacteria in a petri dish is circular. Find the approximate increase in its area if the radius is increasing from 40 millimeters to 42 millimeters. So you start with area of a circle. The formula for that's easy, pi r squared. Hopefully we're all familiar with that. And then again, this is sort of just like this right here. T is the variable of interest because time is what's changing. So we don't have y and x, now we have a and r instead. Those are the 2 variables here. So I get a dA over dt. That's like dy over dt right here. And technically this is 1a, so the derivative of that is just the variable. So it's just dA over dt. And then the derivative of this, the pi is just a constant, so it's you multiply the exponent by the constant, 2 pi, decrease the exponent by 1, and then because the variables are here, then you need a dr over dt. Okay, so find the increase in the area if the radius increases from 40 to 42. So it increased by 2. That's how the r is changing. And it started off as 40. So that's what r would have been. So I've got the 2 pi that are constants. R started off as 40. And then it's changing at a rate of 2 units per time, since it went up from 42 to 40. Okay, so type an answer in terms of pi. So sometimes they would want you to plug something in for pi, but here they don't. So 2 times 40 is 80, times 2 is 160, 160 pi. So if the radius is changing by 2 units, increasing by 2 units over a given period of time, the area of the petri dish is going up by 160 pi square millimeters, because it's a very tiny dish, but 160 pi. So millimeters aren't very big, but these bacteria, they can grow if you let them keep going. They grow exponentially, actually. Okay, so take your famous formula from geometry, find its derivative, and then you're going to have a dr over dt for the r variable, and the question is really finding the change of area. What is the area change with respect to time? If the radius is changing with respect to time as a positive 2. It went up from 40 to 42, it increased by 2, and you always put the starting value of r. What did it start at is what r is. Okay, then we hit chapter 7. So there's 5 problems left, and we did 5 problems in 5 sections in chapter 7. 7.1 through 7.5. 7.1 was indefinite integrals, where you don't have any numbers to plug in. This is antiderivatives, the first time you learn that. 5x to the third. Here we just have a polynomial. Plus 5x squared minus 7x plus 3. So we can do this term by term in a polynomial. And now the process is reversed, both in steps and in order of doing derivatives. In derivatives, you do the exponent times the constant, and then you decrease the exponent by 1. Here it's reversed. You increase the exponent by 1, and then you divide by that exponent instead of multiplying it. And do that each term. So start off with your 5x, increase the exponent by 1, and divide by the new exponent. Minus 7x, increase the exponent by 1, divide by the new exponent. The same way when you have a linear and a derivative and it's just a constant, if you have a constant and an antiderivative, the antiderivative is the linear version of it. And then because the derivative of a constant is nothing, then there could be a constant in this part, and if I took the derivative of it, then it would be nothing. So there's no way, with nothing up here, there's no way to know what that constant would have been. So we just add a plus c to the end of indefinite integrals every time. And it doesn't look like anything reduces here, so I could just leave it like this. Or you could write 5/4 x to the 4th instead of putting it in the top of the fraction. So 5/4 x to the 4th plus 5/3 x to the 3rd minus 7/2 x squared and plus 3x plus c. That's section 7.1, antiderivatives. 7.2 was the u substitutions. There's two main kinds of problems, although a few smaller types of cases, but the two main cases are when you have two parts multiplied together or two parts divided. That's what we have, the divided by 1 here. So in either of those two cases, there's usually one part that has a parenthesis with an exponent attached to it. 10x squared plus 16x. This part has a exponent right here. And it's in the denominator, or it could have been like these two things could have been multiplied to each other instead of divided. But in either of those two main cases, the best u substitution is the entire parenthesis part that's attached to the exponent, without the exponent. So I'm just going to do the inside of the parenthesis, 10x squared plus 16x. I'm going to do the derivative of that and hope that it equals what's already here or some multiple of that. And it's not going to equal it exactly, but it should be a multiple of it here. So 10 times 2 is 20x, doing the derivative. The derivative of 16x is 16. And x is the variable of interest. So I don't have 5x plus 4 dx. I have 20x plus 16 dx. But 20x plus 16 does have a GCF of 4. 20 divided by 4 is 5. And 16 divided by 4 is 4. So there's what I have. That's what I have in my problem. I have everything except for this extra 4. If there's an extra constant in the problem, you just pull it out front. If there's an extra constant in the du statement, then this is where we need to insert both a 1/4 and a 4 into the original problem so that we have everything we need. And we can always do the same thing. We can do the same thing and its opposite at the same time to a problem, and it doesn't change what's happening. If I give you $3 and take $3 out of your pocket, you still have the same amount of money, even though it's in a different way. So if I multiply by 4 and divide by 4, in essence, this is dividing by 4. If I do that both at the same time, then I'm really multiplying by 1, which doesn't change anything. But I need all of this to be equal to the du. So the 1/4 is an extra constant now. The top is going to turn out to be du, and the bottom is going to be u to the 4th. And then I can slide the du off to the side if I don't want to put it in the top. And that's usually the better way to write it, because then you have 1/4 integral of u to the -4th du. And again, the whole point of doing this is to get an easier antiderivative to do. I have a single thing now instead of some complicated thing. So now I can do the antiderivative just like the previous problem and increase the exponent by 1 and divide by that new exponent. And then I can put the -3 times the 4 and get -1/12. -1/12. I can substitute the stuff that u is equal to back in. 10x squared plus 16x. Whoops, 16x. And then it has a -3 exponent plus c. And this would be good enough for the answer since it's an indefinite integral. I could make this -3 become a +3 by putting it down in the bottom with a 12 if you'd rather do that. But they'll take either answer. So -1/12, 10x squared plus 16x, and that's to the -3rd power if I write it this way, plus c. Or put it in the bottom and make it +3. And you could do the derivative of this to see if you get this problem back again, because the -3 times the -1/12 would be +1/4. And then you would rewrite this base and decrease the exponent by 1 to a -4. And that's where this part would come from. But then you'd have the chain rule, and you have to multiply by the inside, the derivative of the inside, which is 20x plus 16. And then if you take out a GCF of 4 of that, it will cancel your 1/4, and then you'd be left with just 5x plus 4. So the derivative of this does equal that. You could double check that with the chain rule to see if it works. Okay, section 7.3 was all about these left and right and midpoint rectangles in order to approximate what eventually becomes the definite integral. So 28 f of x equals -x squared plus 9 -x squared plus 9, and from -2 to 2. And then we want n equals 4. That's the number of rectangles. So if you go from end minus beginning and divide either by the number of rectangles or by the width of the rectangles, then you get the other answer. So this n equals 4 is the number of rectangles. So if I divide by the number of rectangles, then I get the width of each one. Sometimes they tell you the width of each one, and then you divide by that, and that tells you how many rectangles you'll have. Well, this minus a negative is plus, so that's 2 plus 2, 4 over 4. There's going to be a width of 1 on each rectangle. So -x squared plus 9 is a graph that looks like this. And when x is 2, those would be 5. So we're talking like right here. Let me call this spot 2, 5. And this would be 2, -2, 5. And then you could get your -1 and your +1, and this would be 0, 9 up here. So first, with left endpoints, I want this f of 2, this f, -2, that should be, this f of -1, then f of 0, and f of 1. I only want those 4. We're not going to go all the way to 2. Those are the 4 left endpoints. The width of each one is 1. That helps because then I can just factor out a 1. And if I evaluate these 4 things, f of -2, f of -1, f of 0, and f of 1, add all these together, and then you multiply by the width of each rectangle, which if it's 1, then that helps because you don't have to worry about it. So f of -2, -2 squared is 4, and then -4 plus 9 is 5, which was this spot right there. And then 2 will equal that 2, but I'm not going all the way out to 2. If x is 0, the y is 9. And if I get 1 or -1, they should both be the same. 1 squared is 1. -1 plus 9 is 8. So I got 1, 8, and -1, 8 are the other 2 spots. So both of these are 8s. So this answer will be whatever this adds up to, 13, 22, 30. The left endpoints give me an answer of 30. Now, because I have a symmetrical graph, and because I'm doing it over a symmetrical portion of its graph, this would be different if I went from, say, like -2 to +1. Then the answers would be different. But because of that, all that you normally do to the right side, the right endpoints, you still have your width of 1. And you don't do this first one. You do these. These are your first 3, actually. They always share those 3. So I'm doing f of -1, f of 0, and f of 1. Those are in both of them. But the right endpoints have f of 2 included. But because the f of 2 has the same answer as the f of negative 2, then I'm going to get the same answer for part B. That's not usually the case either. It's only because of the symmetry of the graph and because I'm going over a symmetrical portion of the graph. But usually the whatever value this one is, usually this one's different. And that means one of them is an overestimation and the other one's an underestimation. But here they're both going to be 30, just out of coincidence. And if you're ever averaging the same number twice, it's itself. The average of the same number is itself. And then the midpoint will have that same answer just by the symmetry of it all. But if you were normally doing the midpoint, you'd want to go halfway between negative 2 and negative 1, which is negative 1.5. Halfway between negative 1 and 0 is negative 0.5. Halfway between 0 and 1 is 0.5. And halfway between 1 and 2 is 1.5. So the midpoint approximation, it would have the one width of each rectangle, and then you would have to do each of those. F of negative 1.5 plus f of negative 0.5 plus f of 0.5 and f of 1.5. And by the square, I can just do the 0.5 and the 1.5 and get the same answer for the negatives. So 1.5 squared is 2.25. And then you make it a negative, and then you add 9. So both f of 1.5 and f of negative 1.5, they both have an answer of 6.75. Because a negative squared has the same answer as the positive squared does. And then I can do the same thing for 0.5. 0.5 squared is 0.25. Make it a negative from this negative right there, and then add 9. So both of those answers are 8.75. So let's see if my assumption was right that this will add up to 30. Nope, it's 31. Okay, good thing I double checked it. So that would be the more accurate answer then, for sure. So the left endpoints are 30. By coincidence, the right endpoints turned out to also be 30. Sometimes these two are different. Most of the time, these two are different. The average of 30 and 30 is definitely 30. But the midpoint is apparently giving me a slightly better approximation. In fact, I could know the exact answer to this by just doing an integral from negative 2 to 2, because the graph is entirely above the x-axis for the portion I care about. And it would be easy to do the antiderivative of this and use the fundamental theorem of calculus, which we're about to do on problem number 29 anyway. So this would be negative x to the third over 3 plus 9x, and then evaluate that from negative 2 to 2. Big F of 2 minus big F of negative 2. This would be the exact area, actually. And let's see how close to 31 it is. So 2 cubed is 8. You'll get negative 8 thirds. 9 times 2 is 18. There's big F of 2. Big F of negative 2. Negative 2 cubed is negative 8, but then this negative would make it positive 8 thirds. And that would be minus 18. So this would be negative and this would be plus. There would be two different plus 18s and then two different minus 8 thirds. See, the actual area is 30.66666. 30 and 2/3. The midpoint approximation is a little closer. 31's a little closer to that. The left and right endpoints, they're pretty close too, but that's just the basis of this. It's not that interesting of a graph just to have it go up and back down again. But yeah, so that confirmed it. You didn't have to do this on number 28, but I just did it out of curiosity. And the actual area would be 30.66666, which 31 is closer to that. And that's what we're going to do on number 29 then. Now, if they say find a definite integral on 29, then you don't care if part of the graph goes below the x-axis. Then if there is any portions below, they just negate out parts that are above, but we don't care about that. So if they say find the area, then you got to worry about is anything below the x-axis or not. So 7x squared minus 8x plus 2. This is more like problem number 26, where I'm just doing the antiderivative, but then I'm going to also plug these numbers in at the end. So the antiderivative of this would be 7x, increase the exponent by 1, and divide by that same exponent. Minus 8x, increase the exponent by 1, divide by that new exponent, and 2 becomes 2x. And this can reduce to 4. And evaluate it from 0 to 4. Big F of 4 minus big F of 0. Big F of 4 would be 7/3 times 4 cubed minus 4 times 4 squared plus 2 times 4. 0, 0, 0. These all have x's multiplied in, so it's going to be all zeros for big F of 0. So I only have to worry about big F of 4. 2 times 4 is 8. 16 times 4 is negative 64. And then 64 times 7/3 doesn't come out exactly. So I got to worry about, do they want decimals or fractions? Apparently they want fractions. If it just says simplify. So 7 divided by 3. 7 divided by 3 times 64 minus 64 plus 8. 93.33333. Math, enter, enter. 280 divided by 3. So the definite integral would be 280 divided by 3. And we would have to look at it closer to see if portions of it are above or below the x-axis. We don't really care at this point if we're just doing a definite integral. But there's about 93 area inside of that, depending if some of it goes below the x-axis or not. So you just do the calculation, 280 divided by 3. So finally, here's that one application problem about the producers and consumers surplus. That's the best application of this for business settings. They give me a supply curve, they give me a demand curve. I want to get the graph first, and then the equilibrium point, and then calculate the two surpluses. So the best thing, especially for part B, is to set these things equal to each other. The supply curve is Q squared plus 12Q. And it does not have a plus anything or minus anything at the end. So that's definitely a parabola that has a 0 y-intercept and curves up because it's positive 1 q squared. And then the demand curve, this one's got a negative q squared at the end. It's 1188. So that's the y-intercept, 1188. Minus 18q minus q squared. So minus q squared goes downward. Here's the point of equilibrium. If I draw a horizontal there and a vertical, I need to know this coordinate because then I'll have the x coordinate and the y coordinate at that spot. Those two numbers are very much needed to finish this. So it says the supply curve is a solid line, and this one is emanating from the origin, so this could be the graph. And this dotted line is going up above 1,000 apparently, so this definitely could be it. This one's definitely wrong because it has the supply curve as a dotted line. That's wrong. Here it has a solid line going up, but it doesn't have a 0 y-intercept. And here it does correctly have the supply curve, but the demand curve doesn't have a over 1,000 y-intercept. So this is definitely graph A. The point of equilibrium comes from setting these two equal to each other. And you'll likely get a positive and a negative answer out of this, and we only care about the positive one. So add this q squared over to this side, you'll get 2 of them. Add this 18q over, you'll get 30. And subtract the 1188, so it can be equal to 0. Those all divide by 2 as well. $594. So it's a little bit hard to tell what multiplies to 594 and subtracts to a 15. So one way to do it is guess and check by looking at the graph. If I blow this graph up, it looks like the x-axis is going by 5s. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. The point of equilibrium is somewhere between 15 and 20. So I can use that knowledge to maybe help here a little bit. 594, so does it divide by 16? That's a number between 15 and 20? No. Does it divide by 17? No. Does it divide by 18? Yeah. So apparently the two numbers I need are 18 and 33. 18 times 33 is how you're getting 594. And 18 and 33 are 15 away from each other. So I can use the graph to help me figure this out. And it's a positive 15, so that means the bigger number has to be positive in the factoring portion. So if I had a positive 13 times a negative 18, that would get me the negative 594. And if I do 33 minus 18, that's how you get a 15 in a subtraction. But then they switch to the opposites when I go to the zeros. And a quantity of my product in business can't be negative. I can't make negative amounts of my product. So I ignore the negative answer. And there's the 18 from the graph. The only x value that matters is 18. These two lines would cross each other again over here on this side of the graph at negative 33, but we just don't care about that. So 18 is the x-coordinate of the point of equilibrium, which I got right here. And I can plug it into either of the two original problems. They both give me the same answer because this is the one of the two numbers are equal to each other. So I'm going to plug it into the easier equation, 18 squared plus 12 times 18. So the y value at the point of equilibrium is 540. That's this horizontal right here, 540. And that's the answer to part B. 18, 540. If I make 18 units of my product, then the price, the profits that I could make is 540, if that's what Y, dollars, demand function, okay. So apparently that's like the profit, $540 of profit. It's definitely money. Okay, so then the consumers and the producers surplus, just remember alphabetically C before P. C is always the top one. So if I want part C is the consumer's surplus, the one that starts with a C. So this is going to be an integral from 0 to 18. They're both going to be from 0 to 18 because that's what the x is going between 0 and 18. So both this one and that one are going to go from 0 to 18. The consumer surplus has the demand curve. The demand curve is above the horizontal. So you write the demand curve first. 1188 minus 18Q minus Q squared, there's the demand, minus the horizontal, which is 540. Demand minus horizontal is consumer's surplus every time. And I could combine the 1188 and the minus 540 and just get one constant of 648. And minus 18 minus Q. Okay. So now do antiderivatives. This would be 648Q. That would be a constant, turn it into a linear. 18Q, increase the exponent by 1 and divide by the new exponent. And then increase the exponent by 1 and divide by the new exponent. And then evaluate this from 0 to 18. Luckily, big F of 0 is going to be all zeros. So this will turn out to be the same thing as whatever big F of 18 is. So I'm going to plug in 648 times 18. 18 divided by 2 is 9. I can go ahead and make that 9 times 18 squared. And then minus 18 cubed over 3. That's big F of 18. And big F of 0 is all zeros, so I don't have to worry about it. 648 times 18 minus 9 times 18 squared minus 18 cubed divided by 3. So it came out to exactly 6804. $6,804 is the surplus for the consumers. So it's like a buyer's market or a seller's market in real estate. 6804. Round to the nearest hundredth, because if it did come out as a decimal, then I would want to do dollars and cents, but it came out to the exact dollar. So then part D is the producer's surplus, which is also going to be a 0 to 18 range. But now you're going to do the horizontal 540 minus the supply curve, because the horizontal 540, that's above the supply curve. This is area between two curves, so you have to do the above one minus the below one. The supply curve is Q squared plus 12Q. But that one's getting subtracted. So if I clean this up and put it in order, I would put the negative Q squared first, then a negative 12Q, and then the positive 540. So this will be negative Q to the third over 3 for the antiderivative, minus 12Q squared over 2, plus 540Q. And evaluate it from 0 to 18. So again, big F of 0 is not going to matter. Whatever big F of 18 is going to be the answer. So I need a negative 18 cubed over 3. And this equals 6. So minus 6 times 18 squared plus 540 times 18. Negative 18 cubed divided by 3 minus 6 times 18 squared plus 540 times 18. This came out to the exact dollar amount also, $58.32. So a slightly better surplus for the consumers than for the producers. So it's a consumer's market instead of a producer's market. They would have the advantage. Okay, so that's the final thing we did in the class too, was the producers and consumer surplus. That was the very end of section 7.5, and that's a good business application too. So we've now answered all 30 questions. Submit this. Did we get a 33? Yes, we did. 33.333. So I got all 10 of those questions correct, 21 through 30. I had a couple of brain cramp mistakes in the first 10, but I got all the last 20 exactly correct on the first try. So now we've seen every problem in the review. And now you can hopefully work these out over the whole week. If you did 1 through 10 on Monday and 11 through 20 on Tuesday, and now this 21 through 30 on Wednesday, then you've covered every problem and know what's on the final. Then you can use Thursday and Friday to study and practice, and maybe do one last trial run of the entire review all in one shot. See how good of a grade you get. Like if I had done all 30 problems in one sitting and got 28 out of the 30 correct, that would be an A, even if I had a couple of brain cramp mistakes. So if you do well on the review, most people, I don't know if you notice this, but a lot of times I see students, they'll get a 98 on the review and a 97 on the test, or they'll get a 36 on the review and a 41 on the test. And I don't know if it's surprising to them that their test grade is very close to their review grade, but it shouldn't be surprising. Okay, so that's the end of this course. Good luck on your final exam when you take that, either on Thursday or Friday.